Okay, so this is going to be just a little bit more involved on nuclear decay, specifically two types, but we'll go through our types real quick again. We remember that nuclear decay was the emission of energy or particles from a stable nucleus, and those energy or particles could be considered one of these types. We have alpha radiation, beta radiation, gamma, or neutron emission. An alpha particle, as you can kind of see from this picture, would be 2 protons and 2 neutrons. They're red and black, just like the original nucleus was, and of course we know protons and neutrons live in the nucleus. A beta particle, we mentioned, was weirdly an electron. Now, where is an electron coming from in the nucleus? Good question. It actually came from a neutron that decayed into a negative electron and a positive proton. The proton stayed behind. Gamma emission is just radioactive energy, and neutron emission would of course be a neutron. So a little bit more about alpha radiation. We just said an alpha particle is 2 protons and 2 neutrons. So since 2 protons and 2 neutrons are what make up a helium nucleus, an alpha particle is often represented, with the He isotope symbol, 4 on the top for mass and 2 on the bottom for number of protons. Alpha radiation, since this is a fairly big particle as far as radiation is concerned, they won't travel far through materials, but they can ionize matter. They can remove electrons from matter because, of course, they are positively charged, so they would want to strip electrons from something. And if they did that, they would of course slow down and lose energy, gaining those extra electrons. But this would make them, somewhat dangerous. Alpha radiation, you wouldn't want to be near that because it could take the electrons, from your body. Beta radiation, on the other hand, we said it is an electron. Okay, well, an electron's, not really its own atom, but we do indicate it with an E. Again, remember the top number is the mass. Well, electron, we didn't consider it to have a mass. So much smaller than the others, it was essentially 0. So the mass number on the top would be 0, and then the bottom number is supposed to be the number of protons. Well, electron isn't a proton. It's sort of the opposite of a proton. So we put a -1 at the bottom. So this is where we said neutrons can form a proton and electron during nuclear decay. Beta particles are fast moving. Since they're smaller, they would travel farther than alpha radiation through matter, but still not very deeply. And of course they can ionize as well. They would be attracted to anything positive and would lose energy when in contact with anything positive. Alright, gamma radiation. Gamma radiation is sort of pure energy. It's very high energy. It's electromagnetic radiation. It is not considered matter. It's just a form of energy, like light. It's a type of light. It would travel deep into matter. Doesn't have an electrical charge, so it would not ionize. But since it is still very high energy, it could cause damage. We talked about how gamma radiation, can be used for cancer treatments, can be used to kill, bad cancer cells. All right, and then lastly, neutron emission is, of course, the release of a high-energy neutron, and those won't ionize since they are not charged, and they can travel deep into matter. Okay, so we're going to talk a little bit more about specifically alpha and beta radiation. Here's sort of a picture indicating how far these types of radiation can travel through different types of matter. Alpha particles could be stopped by paper, beta could be stopped by aluminum foil, and gamma could only really be stopped by lead or concrete. Okay, so here are some example nuclear decay equations, starting with an alpha decay. Now I know this looks a little complicated, but this is really stuff you have seen before. We've got our symbol Ra here for radium. We got Rn for radon. We can look these up on the periodic table. And of course He for helium. But this would be representing our alpha particle. Again, 2 protons plus another 2 neutrons gives us that mass of 4. This 2, 4, He always represents our alpha particle. So checking out radium real quick on the periodic table, you can see radium right here. You know, that, where's that 88 coming from? Okay, well that 88 of course is the atomic number. That's the number of protons that is always in radium. Remember, number of protons won't change for your element. And then the mass at the bottom here says 226, which means that we are talking about the most common mass of radium. So radium is unstable. It will undergo an alpha decay, and when it does that, it loses an alpha particle, which means we lose 2 protons, 2 neutrons, so we lose a mass of 4. So really just treat this arrow as an equal sign and your numbers should add up. 226 equals 222 plus 4. All my mass numbers should be equal. On the bottom, these are my proton numbers. The atomic number, 88 equals 86 plus 2. So as long as we try to make our little equation balance, you know, the left side of the arrow should equal the sum of the right side of the arrow, we would know that we are doing our equation correctly. Here's an example, beta decay. This case we've got carbon, and carbon-14 is of course an unstable isotope of carbon, and of course the mass is 14, so I want to say my mass number should equal 14. 14, arrow, pretend that's an equal sign. 14 equals 14 plus 0. Well, again, where's this 0 coming from? This is the beta particle. Remember, the beta particle is an electron, so it doesn't have any mass, so mass should be 0. And again, the bottom number is supposed to be protons, but it's like an anti-proton, so we say -1. And if you check, you know, your bottom number 6 does equal 7 plus -1. So this all balances out, and when carbon undergoes beta decay, it will turn into an isotope of nitrogen-14. So if you know how those equations work, you can pretty much write your own, so long as we are told if it's beta or alpha, or perhaps in this case a neutron emission. Okay, so bear with me, I'm going to write this with the mouse. It won't look that pretty, but we'll write these out. Okay, so let me just make a little space here, and we'll do number 1 first. Alright, so beta decay for thorium-230. Alright, I'm going to start with the beta part. I should always know what to write if it is beta. So something's going to decay, put my little arrow here, and I know that beta is an electron with -1 protons, antiproton, and a mass of nothing. So I know that that's got to be on the right side of the equation. That's something I end up with. And I will end up with some other element, not sure yet what, but now I need to look up thorium. So let's go to our periodic table for a moment. Okay, so we're looking for thorium. Thorium in our problem has a mass of 230, so it is an uncommon isotope of thorium. But the important number that we need here is 90. The atomic number, or the number of protons in thorium, is 90. So if thorium's atomic number is 90, that should go on the bottom here. That's the number of protons. Sorry for the handwriting. And the mass goes on the top. That was 230, according to our problem. Okay, 230 was the mass we were starting with. So what should we end up with? We know it's beta decay, so we've already written out our beta particle here. We've just got to simply make sure the numbers add up. So 230 equals 0 plus, well, it must be 230 on the top. On the bottom we have 90 equals -1 plus what? 89 or 91? Going to be 91. Okay, and now I should know what element that is. So I got to go back to the periodic table and simply look up what is element 91. Don't look for the mass of 230 because we know masses can change. But 91, the number of protons in this element, should never change. So back to the periodic table for a moment. Okay, so we're looking up atomic number of 91, which happens to be Pa, which is protactinium. Doesn't matter that our mass doesn't match. That could really be anything. But 91 has got to be Pa. So now that I know that 91 is element Pa, I just write that right here, isotope notation. So again, apologize for the handwriting, but that would be how you would write a beta decay equation for thorium-230. Start with your given, thorium-230 right here. Then we're going to have our little arrow for our equal sign. This is telling us what it decays into. Our directions told us it was beta, so I have to write the E with the -1 and the 0. That's always what you would write for beta. And then just making my numbers all add up, I end up with a mass of 230 still, and an atomic number of 91, which was Pa, protactinium. All right, let's try number 2. Okay, number 2, carbon-10. We've got an alpha decay of carbon-10. So again, I'm going to start with the alpha part. Alpha, an alpha particle, I know is 2 protons and 2 neutrons, which has a mass of 4. And of course, I just said it had 2 protons, so atomic number is 2. And that is really represented by a helium nucleus. I'm going to write He. So what I just wrote there is what you would always write for an alpha decay equation. You'd always have the 2, the 4, and the He. So I know I'm starting with carbon, which is C. Okay, I've got the mass given to me as 10, so that goes up top. And carbon, hopefully that's a common enough one we remember. Carbon has an atomic number of 6. We can look that up on the periodic table real quick. So of course there's carbon, atomic number 6. We're not using the common mass of 12 this time, but that's where we got the 6 from. So now that all we have to do left is just make sure our numbers add up. So right here we're saying 10 equals 4 plus what? Gotta be 6. On the bottom, we're saying 6 equals 2 plus what? Gotta be 4. So now I've got to figure out what element this is. Again, I do not look up the mass. I look up the atomic number. I've got to see what matches with 4 on my periodic table. All right, so looking for an atomic number of 4 has got to be beryllium. Again, clearly has a different mass. It must be an isotope of beryllium, but 4, the atomic number, is the important part there. So I need to write down Be. And there we go. There's our atomic decay equation, our nuclear decay equation for carbon-10. Start with a mass of 10. That's split into a mass of 4 for helium, plus the other mass of 6 for beryllium. And we had an atomic number of 6 to start with, so 6 equals 2 plus 4 on the bottom. So that is correct. All right, number 3. All right, for number 3, we're really just filling in this question mark. Now, this is actually not a decay equation. This would be a fusion equation. We've got 2 things, 2 small things coming together, 2 isotopes of hydrogen. But with our common sense and the idea that the mass numbers should, equal out left and right side of this arrow, and that the atomic numbers should also equal out left and right side of this arrow, we can figure out what this question mark must be. So we should easily be able to tell what the top number is. Right here we've got 3 plus 2, which is 5, equals, question mark, plus 1. So 5 equals what plus 1? Got to be 4. On the bottom we have 1 plus 1, of course that's 2, equals what plus nothing? So of course that should be 2. And since we've just done some examples like this, hopefully you already recognize the 2 and the 4 has got to go with an alpha particle, He, which in this case is a fusion example. Like in the sun and the stars, hydrogens will fuse into a helium. And in this case, we have an extra neutron emitted. All right, one more, number 4. All Okay, so this is definitely a decay equation again. We've got one thing breaking down into two things. We immediately notice our E for a beta particle, so this is going to be beta decay. So simply just making our numbers equal, we've got 18 equals what plus 0? Well, that's got to be 18 again. 18, okay. On the bottom we've got 8 equals what plus -1. Okay, just be careful there. I always get people to say 7. Nope. It's going to be 9. 9 plus -1, 9 minus 1. That's going to be your 8. Alright, so I've got my atomic number figured out. I got my mass number figured out. Now I just simply have to figure out what element that is. So let's go to our periodic table and quickly look up 9. Alright, so looking for 9. 9 must be fluorine. Again, I do not care that the mass does not match. It's the number one mistake I see. We're not looking for a mass of 18 specifically, because it's of course around to 19. We're looking for the atomic number of 9. So, got to be fluorine. So, just need to put an F right here, and that will finish off my answer. Atomic mass of 18 on the top, 9 for atomic number on the bottom, and that must have been fluorine for the question mark. Okay, so moving on, another topic within nuclear decay is something called the half-life. It's pretty interesting. Half-life is the amount of time required for half of a radioactive nuclide to decay, which is kind of interesting that they decay in this sort of rate, half per whatever amount of time. If it's a really unstable isotope, of course, the half-life would be quick. And this is one way we can use to date artifacts, fossils, carbon dating. As an example, carbon-14, for example, has a half-life of about 6,000 years. So let's say you know how much carbon-14 is in a typical human bone, and you happen to find a bone, and you dig it up, and you measure it for how much carbon-14 is in it, and about half the amount of carbon-14 you would find in a normal living bone is there. So if about half of the amount of carbon-14 is there that we expect, then we know 6,000 years has passed since that animal died. So here's an example again. Let's say an original sample, so the bone of a dinosaur, the bone of any animal. Let's pick a wolf. So let's say the bone of a wolf, typical living healthy wolf, has 8 isotopes of carbon-14 in it. Okay, well then that wolf's going to pass away. And if we find its fossils and we dig it up and we realize that there's actually only 4 isotopes of carbon-14 in that bone, well, we realize one half-life has gone by. So of course that'd be, again, if it's carbon-14, about a 6,000-year-old bone. If we dig it up and we find there's 2 isotopes of carbon-14 left, then 2 half-lives have gone by, because we're always decreasing by half. So another 6,000 years has gone by, so this must be a 12,000-year-old bone. And you can keep going. If we decrease that by half again, another 6,000 years would have passed. So that would be, what, 18,000-year-old bone. So here's 2 half-life problems. Okay, so here's a half-life problem. The half-life of radon-222 is 4 days. What was the original mass of a sample of radon if 0.05 grams remains after 12 days? Alright, so the way I like to do this is I like to set up a little timeline chart. So on the bottom we're going to have mass. Alright, and then on the top I'll put time. Alright, and in this particular case I'm starting at the end. I know the very end was 12 days. going to put that down here. And I know at these 12 days I had 0.05 grams. So I just basically want to just keep backing it up. Now a half-life is 4 days, so I'm going to back this up in sets of 4. So 12 minus 4 would be 8 days. So at 8 days, how much of the sample actually existed? Well, bear in mind it simply just decayed into the 0.05. So instead of taking half, we're going backwards. We've got to start doubling everything. So this must have been 0.1 gram. So at 8 days, there was 0.1 gram. Another half-life goes by here to 12 days. That's 4 days that goes by. That's a whole half-life. I cut my sample in half and I get to 0.05. Okay, so still backing it up. So another half-life before that, again, each half-life is 4 days long. So minus 4 minus another 4 is going to be 4 days. And how much of my sample did I have after 4 days? Well, if it just decayed in half to 0.1 gram, what was double that? Must have been 0.2. So at 4 days, I have 0.2 grams. Okay, and then the original mass was the original half-life before that, so that was at time 0. Well, I must have had double what I have here, so that must be 0.4 grams. Should be my answer. And we can double check. So if this is what I originally started with at time 0, 0.4 grams, when one half-life goes by, I will have half of that, 0.2 grams. And one half-life is 4 days long. Another half-life goes by, I have half of that, 0.1 grams. And that is again another 4 days long. So that's 8 days. Another half-life goes by, I've got half of that, that's 0.05 grams. Another 4 days, that's 12 days, that's where we ended up. So this was sort of working backwards, but our final answer here should be 0.4 grams. Okay, let's try number 2. It says if a typical human bone contains 20, and this was our mu, Greek letter mu, but it stood for micro, 20 micrograms of radon, how old is a bone that contains 2.5 micrograms of radon? All right, so I'm going to do the same thing. I'm going to set up a little time chart, put time on the top. And let's look at our information again. We want to know how old is a bone that contains 2.5 micrograms of radon. And a typical human bone contains 20 micrograms of radon. So we're starting at 20. And we're starting at time, 0 again. Always start your stopwatch at 0. So one half-life goes by. One half-life. How much radon would we have left? Well, divide it in half. We'd have 10. Keep on going. Another half-life goes by, we would have 5 grams. So that'd be 2 HLs. All right, and then another half-life goes by. We're just going to divide this in half again. We would have 2.5. So that is 3 half-lives, which is our answer. If we remember the information from problem number 1, it did tell us what a half-life of radon was. It said every half-life was 4 days. So if we want to throw that into our chart, we would know that it is 4 days have passed when it's 10 micrograms, 8 days have passed when it's 5 micrograms, so this must be 12 days, or 3 half-lives. Okay, so I would just pause it here and try these on your own. You're just trying to fill in what the A, X, and Z are. Of course, the A and Z should be numbers, X should be some letters for whatever element it is, and then write if it is alpha or beta. So pause it, take a second to try those on your own, and then I'll put up the answers. So here are your answers. Number 1 is beta decay, 2 is alpha decay, number 3 is also beta decay, of course, because of the electron there, but the answer should have been copper with a mass of 63. Atomic number, of course, always for copper is 29. And the last one is also alpha because we have that helium here. This is actually TL, this is not TI, that is thallium with an atomic number of 81 and a mass of 208. Okay, so here's our last set of practice. These are some more half-life problems, and they are set up a little differently. So again, I would pause and try them on your own, but I'm going to put up the answers here in just a second. Okay, so there are your answers, but these problems are just a little bit different than the other ones we did in the notes. So I will sort of set them up and try to explain how I did them. Okay, so for number 1, of course, I'm going to set up a little timeline chart. This is different, again, because it asks for a fraction here. How long will 3/4 of a sample take to decay? So we don't know the actual mass that we started with, but let's say, again, we're going to start with time 0, and at time 0 we have 100% of the mass left. All the mass is there, 0 of it is gone. So after 1 half-life goes by, that's going to be 8.1 days, we will have half of our sample left. And if half is left, well, half is gone. So we go on again. So next half-life would be another 8.1 days. That's going to add up to 16.2 days total. That's 2 half-lives. And after 2 half-lives, then 1/4 of our original sample would be left, and so if 1/4 is left, then 3/4 is gone. And that's how we got our answer there of 16.2 days for number 1. Okay, let's try number 2. Number 2 says radon-222 is a radioactive gas with a half-life of 3.82 days. How long will 15/16 of a sample of radon-222 take to decay? Alright, so I've got my little chart. At time 0, I have 100% of my mass, 1 full amount of it. After 1 half-life goes by, that's going to be 3.82 days. I will, of course, have half of the mass. Alright, keep going. Add another 3.82. That's going to be 7.64. And at that point I will have 1/4 of the mass. Still going. Next I will have 11.46 days to have passed. Again, I'm just adding the 3.82 days each time. And now I'm down to 1/8 of my sample. And still going. We're trying to get to 15/16 are gone. So add another half-life, 3.82 days. That's going to get you to 15.28. If I can make an 8 days, and here we would have a 16th left. So if we have a 16th left, then the other remaining 15/16 are gone, And that is how we got to 15.28 days. Okay, number 3, also a little different because they ask for a percentage. It says uranium-238 decays very slowly. Its half-life is 4.47 billion years. What percentage of a sample of uranium will remain after 13.4 billion years? All right, so what percentage? So we'll stick with our fractions for now and turn it into percentage at the very end. So of course, starting at time 0, we have 100%, one full amount of our sample. We're going 4.47 billion years at a time. So after 4.47 billion years, we're down to half. And then let's add another 4.47 billion years. So that's going to be 8.94. And then we would be down to a quarter of our sample, a fourth. And we're trying to get to 13.4 billion years, which is our next one. One more half-life down the road is 13.41 billion years is going to give us an eighth of our sample. So we know we have an eighth of the sample left after 13.4 billion years. That's 3 half-lives that have passed, 1 half-life, 2 half-lives, 3 half-lives. So how do we simply turn that into a percentage? So if you want to turn that into a percentage, you just divide 1 divided by 8, and you will get a decimal, but that's okay, 0.125, but you guys know how to turn decimals into percentages. Simply move that decimal twice, and that's how we got our answer of 12.5%. Sorry. All right, number 4, looking at the same chart, a sample of strontium-90 is found to have decayed to 1/8 of its original amount after 87.3 years. What's the half-life of strontium-90? All right, well, it tells me an eighth, so I'm going to just mark that off on the bottom. After 1 half-life goes by, again, I've got a half. Another half-life goes by, I'm going to have a fourth of that sample. And another half-life goes by, I'm going to have an eighth. So I kind of need to go backwards here, but after I have an eighth left, 87.3 years has passed. So what is 1 half-life? So we just need to figure out what 1 half-life is. Well, it took us 1, 2, 3 half-lives to get to 87.3 years. So if I want to know what that increment is, I just have to divide by 3. And 87.3 divided by 3 is going to equal this 29.1 years. So that would be 29.1. If I wanted to fill in this, I would just add in another 29.1, which would be 58.2. But the answer for 1 half-life was 29.1. All right, those are some example problems. Go back through those, a little tricky. Hopefully you'll get the hang of it after a few practice bell work problems. But that was nuclear decay, talking about alpha decay, beta decay, and then half-life problems. The end.